Today is the 4th of December, the feast of Saint Barbara. 151 years ago on this day Adolf von Baeyer discovered how to synthesize barbituric acid, the parent molecule for barbituric sedatives, all named after Saint Barbara. So in honor of the German chemist and to commemorate the day, we're going to synthesize barbituric acid using the diethylmalonate we prepared in the previous video. First we're going to get it as pure as we can by distilling it. We've got about 10 ml of diethylmalonate here in a small flask, and we've set up for simple distillation. It's really important to use pure reagents for this reaction, as well as being extremely careful to ensure that all reagents and apparatus are dry. We're using the thermometer so we can check the temperature of the vapors and make sure we save only the pure diethylmalonate, which boils at around 200 degrees C. We're heating and the liquid starts to crackle at first, a bit like a hot oil bath. We start to collect a small amount of liquid, only about 1 ml or so, at around 80 degrees C. This has a very characteristic aroma and is ethyl acetate, an impurity due to acetic acid being present in our previous esterification mixture, probably due to malonic acid decomposition. Then the temperature increases and we start to get a main liquid vapor front coming up the glass. The temperature shoots up to about 140 degrees C and we get a few mL of a rather unpleasant smelling liquid coming over. Then the temperature increases again and we get distillation of a clear, fruity, sweet smelling liquid at above 190 degrees C. This is our pure diethylmalonate distilling. In order to ensure the pure product, we didn't complete the distillation, but collected enough of the liquid that we could work with. We didn't want any decomposition products potentially forming and coming over, making our distillate impure again. Here's our starting material. Exactly 4 grams of fruity smelling diethylmalonate, which is a slightly oily liquid. We placed this into a small dry beaker and reserved it ready for the reaction. Okay, here's our reaction setup. We're using a hot plate for heating and a small flat-bottomed flask sitting on this. At the moment we don't have a magnetic stirrer in there, but we recommend that you use one, as you'll see later on. We've got a smally big condenser attached to the flask, and on top of this we've got an adapter connected to a drying tube containing anhydrous calcium chloride. It is essential that all the glassware is completely dry. Oven dry everything, then assemble the apparatus while the glass is still hot, then leave to cool. Let's get going. First we've measured out 20 ml of absolute ethanol into a dry measuring cylinder. Again, the ethanol must be anhydrous for this reaction to work. With the condenser temporarily removed, we add this into the flask. Okay, here we go. We've closed it back up again to ensure that no moisture gets in. Now we've measured out a block of sodium metal weighing around 1.5 grams. We're going to use a sharp knife and quickly trim the sides to remove any oxide, any hydroxide buildup. Then we quickly add the remaining sodium block weighing just over 1 gram to the flask. This reacts with the ethanol and bubbles away, producing hydrogen gas. The mixture also heats up and starts to reflux very slightly. The sodium metal takes an hour or so to dissolve, and towards the end it helps to switch on the heat so that the mixture refluxes. Okay. While we're waiting for this to react, we're going to prepare the other reagents we need for the reaction. In this reaction, diethylmalonate condenses with a molecule of urea to give our product. We took some urea powder and placed it into a makeshift desiccator containing anhydrous calcium chloride for a few days in order to make sure it was completely dry. Then we weighed 2.2 grams of the dry urea powder into a dry beaker, and added 15 ml of absolute ethanol. We've got the hot plate switched on and we're now going to heat the urea and ethanol until the urea goes into solution. We've covered the top of the beaker to stop moisture getting in. The urea will dissolve, but it requires the ethanol to be nearly boiling. And here's our diethylmalonate from the distillation we did. We've placed it into a small beaker with a few granules of anhydrous calcium chloride to make extra sure it's properly dry. Our sodium has now completely reacted and we've got a slightly viscous cloudy sodium ethoxide solution now. So first we add the diethylmalonate to the reaction flask. And now we're just waiting for the urea to dissolve in the ethanol. That boiling point, that's all dissolved. And now our urea solution in ethanol goes into the reaction flask. Within about 10 seconds a white precipitate starts to form in the flask. And this becomes quite thick. So now we need to heat the flask to reflux temperature and keep this going for a few hours in order for the reaction to complete. There's just one catch. The ethanol and the heavy precipitate create a mixture which bumps very violently. To counteract this we place a small magnetic stir bar in the beaker and set it stirring at high speed. This didn't stop bumping entirely, but it does reduce the magnitude. We left this to reflux gently for the next 2 hours. There wasn't any further visible change to the reaction mixture during this time. It's still a relatively liquid slurry. During the last 15 minutes we prepared a beaker containing 20 ml of water, and placed this on the hot plate. When the temperature of the water is about 60 degrees C, then it's ready. 2 hours are now up, and we've removed the drying tube from the condenser. As you can see from the indicator paper, there's an alkaline reaction from the vapor. This is due to a small amount of ammonia being formed in the mixture as a result of urea hydrolyzing under the alkaline conditions. However, there's not much. Now we add the warm water to the flask through the condenser. There's no obvious reaction or heat evolution. We allowed the mixture to cool slightly and then dismantled the majority of the apparatus. Okay, our product should be in this mixture, and since it's acidic it will be dissolved as the sodium salt. Here's about 8 ml of concentrated hydrochloric acid in a small beaker and with a dropper so we can add it to the reaction mixture. On addition, the white precipitate starts to become lighter in volume. The mixture at this stage is still strongly alkaline, as you can see from the indicator paper. So we keep adding the hydrochloric acid slowly. And soon the precipitate disappears, forming a clear solution. Now the mixture is strongly acidic, so we're finished with acidification. Our product should now be present in the solution as free barbituric acid. This is still somewhat water-soluble, So in order to get it to crystallize, we need to chill the solution down to nearly freezing point for an extended time period. After only an hour or so of chilling, some white crystals are already visible in the mixture, as you can see. Let the mixture chill in the coldest part of the fridge, but without freezing, for 6 hours. Here we are 6 hours later. The cream-colored solid has fallen to the bottom of the flask. So we set up for filtration. We're using our grade for fine sinter, as it looks as though the crystals are quite small. We wash with a small amount of ice water and then let them to dry thoroughly on the pump. Here's our dried product. 2.3 grams of fluffy cream-colored tiny crystals of barbituric acid. Barbituric acid is colorless, so this will need recrystallization to obtain a completely pure sample. This is a crude yield of 72%, which is about the same as the literature suggests, and this is a great result as it shows our drying precautions worked well. Here's a small amount of water in a beaker. Let's add some of the product. Some dissolves, but as you can see, it's not that soluble. Now let's add a little bit of sodium hydroxide. Now the solid dissolves, forming the sodium salt of barbituric acid in solution. Overall, a very satisfying experiment, and it was by sheer coincidence that we had the opportunity to do it at exactly the right time of year. Depending on who you believe, that is. Thanks for watching, and stay tuned because it won't be long before our 100th video, and we've got something special planned.